Welcome to this lecture video on Taylor's theorem. Okay, so first I want to discuss the relationship between the coefficients of a power series and the function that it represents. So this will be coefficients of a power series and the function it represents. Now we'll give a rigorous definition of what it means for a function to be represented by a power series a little bit later on in the lecture. But from now, you can just take it to mean, suppose this power series converges on some interval, right, an open interval, and say we just write the function that it converges to as f of x. F of x is the limit, right, of that power series, the pointwise limit. We know that power series are infinitely differentiable. That's one of the properties of power series. So that means that you can take as many derivatives as you like, and we can also integrate them, right? Every time you integrate a power series, you get another power series. Every time you differentiate a power series, you get another power series. So in this way, power series are infinitely integrable and infinitely differentiable, okay? Now, of course, this is only true if your radius of convergence is greater than 0. So if your radius of convergence is equal to 0, then you're only converging at a point. So you can't take the limits required for differentiation, right, if you're only valid at a point. Okay, so here we are. What is the relationship between each coefficient a sub n and f? And the way to see this is basically, let's have a new page here. So if we have f of x as, and I'm just going to write out a naught plus a1x plus a2x squared plus dot 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 plus a sub n x to the n. Then when we take, the first thing we notice is we can single out a naught by simply setting x equal to 0. So if x is equal to 0, then the remainder of these terms are going to be equal to 0. And a naught, therefore, is going to be equal to f of 0. So f of 0 equals a naught, right? And we can kind of do this again by noticing that the derivative of f with respect to x, so f prime of x is going to be, now remember we have our theorem that says we can just do term by term differentiation. So derivative of a naught will be a constant, derivative of a constant, which is 0. The derivative of a1 times x will just be a1. This will give me 2a2x, dot, dot, dot. That will be n, a sub n, x to the n minus 1, right? So let's go ahead and I'm going to switch from this longhand notation to just using my sigma notation because it is more compact. But if you have trouble with the sigma notation, it's okay. You can just write out a few terms and then plus, 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 dot, 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 write out the nth term plus dot, dot, dot. And in that way, you can figure out the pattern and you can, go back and forth between sigma notation and writing it out longhand. So when I take the derivative, I'm going to get n times a sub n, x to the n minus 1. N will start at 1. And I notice that if I plug in x equals 0 to f prime of x, so f prime of 0 is going to equal a 1 plus 0 plus, right, all the other terms will be 0. So f prime of 0 is just going to be a 1. And I can take the derivative again and get f double prime of x is going to be the sum n. This time I'll have n minus 1, a sub n, and then x to the n minus 2. N is starting at 2. And now, if I plug in x equals 0, all of the terms will fall away except for 2 times 1 times a sub 2. So 2a sub 2 is equal to f double prime of 0. Okay, and I can continue this and take the nth derivative, and I will get the sum, or let's just not say the nth derivative, let's say the kth derivative of f, and I'll get n times n minus 1 times n minus 2 all the way up to n minus k minus 1, a sub n x to the n minus k, and this will start at k. So when I plug in x equals 0, I'll get that the kth derivative of f at x, all the terms will fall away except for when k is equal to n is equal to k. So I'll get just this times a sub n, or a sub k. So the kth derivative at 0 is going to equal n times n minus 1, all the way up to n minus, if n is equal to k, evaluated n equals k. So I'll have k times k minus 1, k minus 2, all the way up to k minus 1. So let's see here. Maybe it should be, there should be parentheses here, I think. Okay. So now all the way down to 3, 2, 1, a sub k. Okay. So I'm able to see that I now have a formula. The formula that I have that determines the relationship between the coefficients of the power series and the function it represents is as follows. A naught is f of 0. A1 is f prime of 0. A2 is going to be f double prime of 0 over 2. Right? And then AK is the kth derivative of f at 0 divided by, and then that's just k factorial, because all of this is equal to k factorial. So my overall formula looking at this is that a sub k will be equal to the kth derivative at 0 divided by k factorial. Okay. This should sound familiar because these are the coefficients of the Taylor series for the function. Okay, so I'm just doing a do not disturb there. All right, so you should have seen, this formula before. This should not be brand new. But let's look at the inverse of that question. Suppose you have a function that is differentiable, right? What can you say, or it's infinitely differentiable? The question is, what can you say is the relationship between it and the coefficients of its power series? Well, from what we've shown, if you have a function and it's equal to this power series, right, then, on an open interval, then the coefficients have to be those nth derivatives, right? Now notice that there's nothing really special about us having our function centered at 0. We could repeat all of this having the function centered at any point C. So for instance, if we had a power series and our f of x were equal to, let's say here, a sub n x minus c to the n, say this were our power series, right? Then we'd be able to say, oh, okay, well now f of c is going to be a naught. F prime of c f prime of x, again, would be n a sub n x minus c to the n minus 1. So f prime of c would be a1, and so forth and so on. So a sub k would be the kth derivative at c divided by k factorial. Okay. So now let's consider a function, and we'll ask under what conditions is f represented by a power series. So suppose you have all of the derivatives, right? If f of 0, f prime of 0, f double prime of 0, the third derivative at 0, and so forth and so on. If all of these all exist, do we know or can we conclude that this power series, based on these coefficients, converges to f? On some open interval, right? So that's the question. Let's look at the big picture here. So say you're given a function f, and f is defined on some interval some open interval. C is in between A and B. So the first question you can ask is it possible to compute all of the derivatives of f at C? So f prime of C, f double prime, f triple prime, do you have all the derivatives? If you don't have all the derivatives, then f doesn't have a Taylor series. You can't go any further, right? You might be able to say that f has Taylor polynomials up to the number of derivatives that you have, but you certainly don't have a series because you need all of the derivatives of the function at C in order to form the Taylor series of the function at C. Okay, but now suppose you do have all of the derivatives, then form the Taylor series of f at C. That is the Taylor series is that power series that's based on those derivatives, right? So you take the nth derivative at c over n factorial, and then x minus c to the nth power. This would be the Taylor series of f at c. So form the Taylor series, and now we've got a question, right? The question is, does this Taylor series approximate f? So the question naturally is f of x equal to its Taylor series? Ooh, undo that. Sorry, something's wrong with my pen. Right? And to answer that question is the same as answering, does the remainder tend to 0 as n tends to infinity? So let's go back and look at and think about what it means for our series to converge, right? So a series converges if and only if its sequence of partial sums converges. So if we look at this like so, our series, so the Taylor series, converges to f of x if and only if the sequence of partial sums converges to f. So now the sequence of partial sums means we're going to n. Okay, so k is going to range from 0 to n. So if this goes to f of x, right, and this would be for all x in your domain, and this would be as n goes to infinity. And that is true if and only if the difference between them goes to 0, right? So that's true if and only if the difference goes to 0 as n goes to infinity. This difference is the remainder. And so we might even switch it around, because you might say the remainder is the actual value minus the estimate. So the estimate is your nth partial sum, right? And we're looking to see if our remainder, i.e. the actual minus the estimate, goes to 0 as n goes to infinity. So here we are. You have your Taylor series for f, but the question is, does your Taylor series represent your function? Well, that's asking the question, does the remainder tend to 0 as n goes to infinity? So we have an inequality that gives you an estimate for the remainder. And if you can show that this inequality goes to 0, the estimate goes to 0, then you can say, oh, okay, well, my remainder goes to 0, and therefore my Taylor series converges to my function f. Okay, so my Taylor series represents my function. But now, here we go. Suppose your remainder doesn't go to 0. Then that means you're done. Your function has a Taylor series, but it's not represented by its Taylor series. Okay, so the Taylor series doesn't converge to the function. Okay, and if you try to use the Taylor series in place of the function, it won't work. You can't reliably do that. You'll get misleading answers because your Taylor series is converging, but it's not converging to the function that you want it to. Okay, so a key example for this would be the bump function. And I think I give you a homework problem on this, but it's a bump function, and it's something like f of x is e to the minus 1 over x if x is not equal to 0, and 0 if x is equal to 0. And so what happens is you could compute all of the derivatives of f at 0, and they're equal to 0. So you're able to form the Taylor series, but the Taylor series is just a 0 function, whereas this function right here is not the 0 function. So your Taylor series doesn't converge to the function it's supposed to represent. Okay. On the other hand, suppose your remainder does go to 0 as n goes to infinity, right? That means, good news, f is represented by its Taylor series. That's a good thing. And we can use the Taylor series to make computations easier. So basically, this means you can approximate f by a polynomial. Right? And it'll be pretty accurate. Because you can approximate anything by a polynomial if you want to. The question is if your approximation is accurate, right? How accurate is your approximation? So you can reliably approximate f by polynomials, and that's great because polynomials are super easy to integrate. Polynomials are super easy to compute. Polynomials, it's easy to compute limits of polynomials, right? So knowing that your function is represented by a Taylor series allows you to do lots of computations quickly, and more easily. Okay, so that's the big picture. This is why we care about Taylor's theorem. That's the title of this lecture, Taylor's theorem. Taylor's theorem gives us information about when the Taylor series represents the function. Okay? All right. So let's go ahead and we're formally giving the definition of the Taylor series for a function about a center C. And C just stands here for center, right? So you think of it as C as the center of your domain of interest, okay? So this is the same definition that we had before. And you might have seen from before, the partial sums of the Taylor series are called the Taylor polynomials. So Taylor polynomials are the partial sums of Taylor series. Okay. So anytime you're talking about a series and you're trying to see if it is going to converge to a function, the way to assess that is to look at the remainder. So you'll have your nth partial sum, and then you'll have your remainder, your nth remainder, and those together are equal to the Taylor series. So if you want to see how well your Taylor series is approximating, if your Taylor series is equal to or converges to the function, you look to see if this converges to f of x, right? Which is the same as the remainder going to 0. Okay? So your partial sums converge to f of x if and only if the remainder converges to 0. And the remainder, of course, is f of x minus the nth partial sum. Okay? And this should be c here. So it's the kth derivative evaluated at c. Okay, so now, this is what I just wrote. So for any point x, your Taylor series is equal to, your Taylor series is equal to f, i.e., the partial sums converge to f if and only if the remainder goes to 0. Okay? So now let's get into the big result for this lecture. It's called Taylor's theorem. So Taylor's theorem says, suppose f is defined on some interval AB and C is a point in the domain. Okay. Also suppose that the nth derivative exists on AB. Then for each x in your domain, that's not equal to C, of course, we can find some y between x and C so that the remainder is actually equal to the nth derivative at y over n factorial times x minus c to the n. Okay, let's go ahead and figure out a proof for this. And I'm going to start just by writing my hypothesis. So for my hypotheses, I actually have several. I'm going to have that f is a function from AB to R. And C is a point in the domain of f. And also that the nth derivative of f exists at each point in the domain of f. Okay? Then the claim is that, and this perhaps I might need more space here. So let me try to make some space. So my claim is that for each x in AB, such that x is not equal to c, there exists a y between x and c, such that the remainder is actually the nth derivative at y over n factorial times x minus c to the n. Okay? So now before we get into the proof, let me just point this out. We always have that f of x is equal to, and I can take it and write it as the nth partial sum, or the n minus first partial sum. So, okay, it's going to go from 0 to n minus 1. X minus c to the k, right? So that's my estimate plus the remainder, which would be f of x minus this. So this is the estimate. This is the remainder that I get when I try to estimate f by that n minus first partial sum. Right, so this is my leftover / remainder of using that estimate. This is my estimate. So we're estimating f of x by the n minus first partial sum of the Taylor series. Okay, so Taylor's theorem is saying that there's some value y where this is actually equal to all of this, right? So in other words, let me make this smaller. So Taylor's theorem is asserting there exists a y in between x and c such that f of x minus that sum is really equal to the nth derivative at y over n factorial. Okay? And a way to write that would be to say f of x is actually equal to this plus this. Right? So for this polynomial, that should be a k. This polynomial, you're taking the derivative at c, right? You're taking higher and higher derivatives at c to build this polynomial of degree n minus 1. And we're saying that f of x actually is, you can find a value where the nth derivative plugged there. We'll go ahead and make f of x equal to this nth degree polynomial evaluated at x. So one thing to point out is that the y depends on x, okay? If y didn't depend on x and the same y worked for all of the values of x, then we'd be saying the f of x has to essentially be a polynomial, right? And we're not saying that. What we're saying is that for each point x in that domain, you can find a y where f of x is represented like this, okay? So let me make that very clear. This y depends on x. It's a function of x, okay? So let's look at the statement of Taylor's theorem for n equals 1, okay? So for n equals 1, Taylor's theorem says if f goes from AB to R, C belongs to AB, f prime exists on AB, then for each x in AB that's not C, okay, there exists a y between x and C such that well, let's see here. What would R1 of x is equal to f prime of y over 1 factorial times x minus c to the 1. Okay, so that would be saying R1 of x is going to be f prime of y times x minus c. Now, what is R1 of x? Well, go back to our definition of the remainder, right? R1 of x, if I look here, that's going to be f of x minus, now plug in n equals 1, so that'll be the sum from 0 to 0, the kth derivative. So this will just be the 0th derivative. So that's just f of c over 0 factorial times x minus c to the 0. X minus c to the 0 is just 1, right? And 0 factorial is just 1. So this is literally just f of x minus f of c, which makes sense because R1 is the remainder that you get when you just use a constant function to approximate your f, right? R2 would be the remainder when you use a line, right? R3 would be the remainder when you use a parabola to approximate f. R4 if you use a cubic, right? So for us, R1 is just f of x minus f of c. So this is going to be f of x minus f of c. So really, we're saying f of x minus f of c is equal to f prime of y times x minus c. Does this look familiar? Does this remind you of anything, right? Saying there exists a y between x and c such that f prime of y is equal to this difference quotient. Aha! Egad! Wow! The MVT Taylor's theorem for n equals 1 is simply the mean value theorem. Isn't that cute? Okay. So this gives us a way to think about Taylor's theorem kind of differently. Taylor's theorem is a generalization of the mean value theorem. Okay? So mean value theorem is your guaranteed existence when you're taking your function and approximating it by a constant. Okay, well then it's natural to ask, well, what do you know is true if you try to approximate your function by a line, right? Degree 1 polynomial, or by a parabola, degree 2 polynomial, or by a cubic, degree 3 polynomial. That's where Taylor's theorem comes into play. It tells you about the remainder when you try to approximate your function by degree n polynomial. Okay, so now that we've kind of worked this out a little bit and we're a little bit more familiar with what Taylor's theorem is talking about, let's go ahead and get into the proof, okay? So for our proof, I'm going to just copy what I have right here. I'm going to copy the setup to my formal proof. And let's go ahead and start with a new page. And let's go ahead and get started with our proof. Okay. So the first thing we're going to do is we're going to consider a helper function. So you'll notice perhaps that the proof of Taylor's theorem kind of mimics the proof of the mean value theorem. For the proof of the mean value theorem, we looked at, if you recall, it was something like, f of a. And so we looked at the function that was f of x minus that line segment, right? And the line was constructed to have the same slope as what we were trying to show the derivative was needed to be equal to. Okay, so we're going to do the same thing here. We're going to consider f of x as the part that we know, right? So this is going to be our n minus first partial sum plus m, we don't know what m is, times x minus c to the n over n factorial, right? So take m, of course, is going to be f minus this times n factorial and divided by x minus c to the n, right? That's what m is going to be equal to, okay? But it'll turn out that this m will be part of a function whose derivative equals 0 will imply our claim, right? Will imply that we'll have a y satisfying this. Okay, so we're going to consider this, and we want to show there exists y between x and c such that m is equal to the nth derivative of f at y. Because if we do that, if we can show there's an m, then this then take that, let me see. Oh, yeah. This would be equal to this, and then this is this part right here, right? So our nth partial sum plus the remainder, that's our r sub n of x. So we just need to show that there is a y such that the nth derivative of f at y is equal to m. Okay, and now here's the approach. The approach that we'll use the approach that we'll use is as follows. Consider g of t, which is going to be defined as this sum over at c over k factorial t minus c to the k plus m times t minus c to the n over n factorial. And then I need minus f of t. Okay, so really, g of t is this polynomial in t minus the original function, okay? And there'll be some things that are true about g. First of all, g of c is equal to 0. Now, how do we know that? Well, g of c is going to be equal to, I'm just going to copy this. And replace t with c. Okay, that's going to be equal to 0. This will be equal to 0 except for when k equals 0, right? So this is just going to be the 0th derivative at c over 0 factorial times 0 to the 0, which is 1. That's 1. That's 1. That's just f of c. So we'll have, oh yeah, and that should be a c. So we'll have, this is f of c. This part is 0. And then we have minus f of c. So all in all, this is going to equal 0. Okay. Now, that's true. We're going to write a couple of facts here. The second thing that's true is that the derivatives of g at c are all equal to 0. Now let's see why this is true. So if I look at my formula here, I think I wrote it down here. So this is g of t. So now g prime of t, for instance, is going to be, if I take the derivative here, the k is going to come down, right? So the k and that k factorial. So I'll have the kth derivative at c over k minus 1 factorial, t minus c to the k minus 1. And I'll start at 1. Okay, and when I take the derivative here with respect to t, I'll get plus m times t minus c to the n minus 1 over n minus 1 factorial. Okay, and then minus f prime of t. So what is g prime of c? Well, that will be, if I plug in c here, these terms will be 0 except for when k equals 1. So I'll get f prime of c plus, if I plug in a c in the second term, that will be equal to 0. So all of that's going to be 0. And then I'll just have minus f prime of c, which will be equal to 0. And I can do the same thing, g double prime of t, sum k equals 2, n minus 1, kth derivative at c over k minus 2 factorial, t minus c to the k minus 2 plus m t minus c to the n minus 2 over n minus 2 factorial minus f double prime of c. G double prime of c is going to equal, well, that term's going to go to 0, and all these terms are going to disappear except when k equals 2. So I'll have f double prime of c plus 0 minus f double prime of c. Sorry, f double prime of c, right? Which is equal to 0. And you could, you come up with the formula for the jth derivative. So for j less than n, jth derivative at t, it'll be the kth derivative. K starts at j over k minus j factorial, t minus c to the k minus j plus m t minus c to the n minus j over n minus j factorial minus f to the jth derivative of f at t is what it should be. So I'm looking here, and that should be a t. Okay, so that the jth derivative at c will equal the jth derivative of f at c plus 0 minus the jth derivative at c, which will be equal to 0. So basically what we've done here is look at the polynomial that best fits the function at the point c. So if you think back to what we were doing kind of in the beginning here, when we were looking at the relationship between the coefficients of a power series and the function, think about if you have a function defined at some point c, say this is your function here. Okay. Now, f of c is right here, and I can approximate my function. If I only have a constant to approximate my function near c, I'm going to choose the line through just plain old y equals f of c. If I'm allowed to approximate this by a line, I'm going to use the tangent line, right? Something is wrong with my Apple Pencil. I'm going to use a tangent line. And how do I come up with the equation of the tangent line? Well, I need a line, and I need the slope of the line to be the first derivative, right? So the slope needs to equal f prime of c. Now, if I can use a, if I can use a parabola, here I'd probably use some kind of, maybe I'll switch to a different color. Maybe this would be my parabola, and I would want, what would I want to be true about my parabola? I would want the second derivative to match up so that they have the same concavity. I would want the same tangent line, the same point of intersection, and the same concavity, right? When we talk about concavity, we're talking about second derivative. So this is saying, give me f double prime of c. Tangent line means we're talking about slope. Give me f prime of c. point of intersection means we're talking about the actual function. Make sure my parabola goes through f of c, c comma f of c. Make sense? So the higher the degree of polynomial that I can use to approximate my function, the more derivatives I'm going to be matching up. So it makes sense when we get through, when we're dealing with our proof, we have this function g. G is this special, g is that polynomial that is specially constructed to have the same derivatives, right? Minus f of t. So yeah, when we keep taking the derivatives of g, it's going to be 0 because we constructed this polynomial so that its derivatives at c would match up with the derivatives of f at c. Okay? All right. So that's the second fact. Again, we're proving facts about g. The first fact is that g of c is equal to 0. The second fact is that all the derivatives of g at c are equal to 0. And then the third fact, or what we're going to do is we're now going to say, well, hey, look a minute. Wait a minute. Let's look at this. Because g of c is equal to, g of c is equal to 0. Do we know that g of x is equal to 0? Let's look at g of x. I think, yeah, I should have written that down. The third fact is that g of x is equal to 0. So let's go and look at x and see what happens. So let's see here. So g of x would be equal to, let me just go and replace all of the t's with x's. And now go back to our definition of m. F of x is precisely this, right? So let me copy this and put it here. So that's my f. Right? So this is going to be equal to this minus this. Hey, those are exactly the same. Yep, you got it, which is equal to 0. And so now we're ready to say, so g of x is equal to g of c. G is differentiable on AB, right? So by Rolle's theorem, there's some point, there exists x1 between x and c such that g prime of x1 is equal to 0, right? And so now let's just suppose that, here's c. So let's just suppose that x is less than c. X could be greater than c, it really doesn't matter. But suppose x is less than c. That means that there's some x1 where now g prime of x1 is equal to 0. But remember, g prime of c is also equal to 0. G is still going to be differentiable on here and continuous on here because g prime is differentiable on all of this, right? So that means there has to be an x2 in between x1 and c such that g double prime of x2 is equal to 0. So we'll apply Rolle's theorem. to g prime, since g prime of x1 is equal to 0, is equal to g prime of c, and g prime is differentiable on AB, right? So there exists x2 between x1 and c, such that g double prime of x2, right, the derivative of this at x2 is equal to 0. And guess what? We're going to repeat this. So between x2 and c, there has to be some number x3, and g triple prime of x3 is going to be equal to 0. So we'll say repeat this process to get, right, there exists xn such that xn is definitely between x and c, and the nth derivative at g of g at xn is equal to 0. The last thing we need to do is go back and compute the nth derivative of g. So if this is g, the question is, what is the nth derivative of g? So this is g, or sorry, this should be g of x. Sorry, g of t is what it should be. When I take the nth derivative of this polynomial, I'm going to get 0, because this is a degree n minus 1. It's a polynomial of degree at most n minus 1. So its derivative, so its nth derivative will just be 0. Okay. The nth derivative of this is just going to be the nth derivative at t. Okay. That's if I'm taking the nth derivative. And then what about the nth derivative of this polynomial? Well, when I take one derivative, the n will come down to the front, and it'll cancel out that. So I have t minus c to the n minus 1 over n minus 1 factorial. If I do it again, and I'll get n minus 1's canceling out, and I'll have over n minus 2. So when I do that n times, I'm going to end up just getting m. Right? So my nth derivative of g at t is equal to m minus the nth derivative of f at t. So if I have a point whose nth derivative at g is of g at that point is equal to 0, that means that the nth derivative of f at that point must be equal to m. And that, remember, was what we wanted to prove. Okay? So let's go back and look at what we've done in order to actually prove this. The first step, right, our goal was to prove that there is some y in between x and c that satisfies this. Okay? So the first thing we did was we said, hey, let's restructure what we're asking for in the proof recognize that f of x can be written like this. So now we just need to show that there's an m, show that there's some point y whose derivative is the m such that f of x is this, okay? So that became our new goal. In order to do that, we looked at this helper function, which was the difference between a degree n polynomial, right, and f of t. And it was constructed specially so that the derivatives of the degree n polynomial match up with the derivatives of f at c. And then once we did that, we just repeatedly applied Rolle's theorem to show that there exists, right? And basically we used induction to show, or not induction because we only did it finitely many times. We just did it n times. We used Rolle's theorem n times to show that there does exist that point in between x and c where the derivative, the nth derivative of g is equal to, at that point is equal to 0, but that implied that the nth derivative of f at that point was equal to m, okay? All right, so we did it. That was good. That was a long proof, but it's basically looking at Taylor polynomials, right? And showing Taylor polynomials have special properties. So let's look at this corollary here. This is very helpful. I wanted to say very helpful because what this does is this corollary says if you know that your function is bounded by a single constant on some domain, then you can be guaranteed to know that your remainder is going to 0 on that whole interval. So this really tells you that f is going to be equal to its Taylor series. Okay? So again, if f is defined, let's go ahead and set this up. So our hypothesis is that f is defined on AB. C is some point, so f goes from AB to R. C is some point in the interval, in the domain. All of the derivatives exist. So for each n and n, the nth derivative of f exists on AB. In other words, f has a Taylor series. And if all of the derivatives are bounded by a single constant, so if this is true for all x in AB and for all n in n, that's hypothesis, the claim is that Rn of x goes to 0 for all x in AB. And this is as n goes to infinity. And the proof is kind of straightforward. We're going to use Taylor's theorem. This is, in fact, a corollary of Taylor's theorem. Taylor's theorem says that for each n, there's going to be some y where the remainder is equal to the nth derivative of y over n factorial times x minus c to the nth power, right? So we want to show that r sub n goes to 0 for any x. So here's what we'll do. We'll just say fix x. Without loss of generality, x is not going to be equal to c. If x is equal to c, then the remainder is automatically equal to 0 because you don't have any remainder because the center of the power series always converges at the center. So a power series always converges at its center. You're not going to have any leftover. You're not going to have any remainder. Okay, so let's look at this. Fix p, or fix x. X is a point in the domain that's not equal to c. Then this is our formula for the nth remainder. And what's going to be true is for all n, the absolute value of this is going to be the absolute value of that. And this is going to be equal to absolute value of the nth derivative at y times the distance between x and c to the nth power, and all of that over n factorial. But now remember, by hypothesis, this is going to be less than some constant c, right? So c is an upper bound for all those derivatives. So this will be less than a constant. And then we'll have x minus c. Perhaps c was the wrong, maybe I should have the wrong letter. Maybe I should have used m. M for max. Okay, over n factorial. And now we know that factorials grow way faster than exponentials. So this is going to go to 0 as n goes to infinity. So this little quick result gives us a way to easily show that functions are represented by their power series. So let's look at this. We're supposed to prove that e to the x is equal to x to the n over n factorial, okay, for all x and r. And let's get started with that. Now, how am I going to do that? I'm going to try to use this last corollary. So what is, do I have a bound on the derivatives of e to the x? So I'm looking here and my center is 0 because I just have x to the n, right? So that's x to the 0 to the nth power. So my center is equal to 0, okay? Now, so f of x is going to be e to the x, and the nth derivative of x is just going to be e to the x. So we know that the nth derivative is always equal to, the nth derivative of e to the x is always equal to x, e to the x. Now, to use this corollary, what I'm going to do is say if all the derivatives exist and are bounded by a single constant, then this limit is equal to 0 for all x and ab. Now, I'm trying to prove this result for all x and r. I don't have a bound for e to the x over all of r because e to the x, grows exponentially. Ha, ha, ha. But what I can do is I can say fix x in r. Now I'm going to consider the interval x minus 1 to x plus 1. Okay. Then for all t in that interval, the nth derivative, and for all n, the nth derivative at t is going to be less than or equal to e to the x plus 1. So here, this is my m, this is my a, this is my b, right? So the remainder goes to 0 for each x or for each t. In particular, the remainder goes to 0 for t equals x. Okay, so I'm able to give a result for each x and r by simply considering an interval that x belongs to. Fix x look at it as part of some interval, bounded interval. Now I have an upper bound on all of my derivatives on that bounded interval, right? And so now my Rn is going to go to x. So that means that my power series is actually equal to the e to the x. Okay. And just in case it's not clear here, this is the Taylor series of e to the x, centered at 0. Okay. And there's a similar justification, or there's a similar approach for proving sine x is equal to its Taylor series. The only thing here is we have things a little easier because if I look here, my derivatives, so if I let f of x equal sine x, then the nth derivative of x is always going to be less than or equal to 1 and greater than or equal to negative 1. Because when you think about the derivatives of sine of x, they cycle between cosine, negative cosine, and sine, right? And each of those trigonometric functions is bounded by 1. So apply the corollary with m equals 1. Okay? All right. And then now here, prove natural log of 2 is 1 minus 1 over 2 plus 1 over 3 minus 1 over 4 plus 1 over 5. And this looks a lot like, here's the approach. The approach would be this is some power series so this looks like the sum of maybe something like 1 over n and then negative 1 to the n. So maybe this is harmonic series, negative 1 to the n. Negative 1 to the n over n. Okay. So you got to make this equal to a power series being evaluated at some point. So I need this to be equal to some power series a Taylor series evaluated at some point. And it looks like the reason why I'm saying x plus 1 is because I remember natural log. We have a power series for natural log that's like natural log of x plus 1. The derivative of natural log of x plus 1, aha. When I take the derivative, I'm going to get 1 over x plus 1, which is my geometric series, right? Because that'll be 1 over 1 plus x. So that'll be minus x to the n. When x is less than 1. So now, if I integrate this, I should get something for natural log of x plus 1. Natural log of x plus 1. So if I integrate this, I can integrate it term by term. And I'll get x to the n plus 1, negative 1 to the n. But then this needs to be over n plus 1. I think we can still have n starting at 0. So remember how we said that the radius of convergence doesn't change when you're differentiating or you're integrating, but the endpoints may or may not change. So here, for x equals 1, this will converge because I have essentially this right here, right? I've got alternating harmonic series, so it will converge. But if I plug in 1 right here, that's going to diverge. So that's how you prove natural log of 2 is equal to all this. You say, hey, natural log of 2 is really natural log of x plus 1 evaluated at x equals 1. I can take natural log of x plus 1, take the derivative, and I get 1 over x plus 1. I know a power series representation for 1 over x plus 1 because this is can be expressed as a geometric series. To get from this up to here, I integrate. So get from here to here, I integrated term by term. Range, the radius of convergence stays the same, but the endpoints, right, the endpoints matter. I'm looking here, and x equals 1, this will converge. And x equals 1, I end up with this, but with a minus sign. I think I'm off with a minus sign, right? So all I have to do is show that this is really equal to this. The remainder goes to 0 at 1. Okay. Okay, and I think there's a thorough write-up of that example in Ross. So I will refer you to Ross. Make sure you read through the details of working that out in Ross. All right, so let's see here. I just want to talk really briefly, we're wrapping this up, about this different version of Taylor's theorem. So the first version of Taylor's theorem that we gave was basically saying that the remainder, R sub n, under certain conditions, your remainder really looks like this. So you're giving the remainder for Taylor's series in terms of a derivative evaluated at some point. Now we have a version of Taylor's theorem that is the integral version. You're now giving the remainder as an integral. Okay? So you have the same setup. F is defined on an open interval AB. C is some point in the domain. Your nth derivative exists. Now you have to assume that it's also continuous because we want to integrate it, right? And so one of the key properties of integrable functions is that a continuous function is always integrable. So by assuming that our nth derivative is continuous, it's okay for us to integrate it, because if the nth derivative is continuous, then multiplying it by another continuous function, i.e. this polynomial, will result in a continuous function, and we can integrate continuous functions. So this is well-defined. This is a well-defined function of x, okay? So let's see here. The proof goes by induction. The P sub n statement is, right, for induction, you have the statement, the inductive statement, you have your base case, and then after that you say, well, if it's true for n, we'll show it's true for n plus 1, right? So the statement would be, if this, then this. So that's the statement P sub n. So what is the base case for n equals 1? The base case for n equals 1 would be over n equals 1, we're saying if f prime exists and is continuous, then for x we have the integral from c to x. So R1 of x is the integral from c to x of x minus t to the, well, now if I plug in x minus t to the 1 minus 1, that's just going to be x minus t to the 0, which will be 1. And if I have 1 minus 1 in the denominator, 1 minus 1 factorial, that's going to be 0 factorial, which is defined as 1. So all of this will turn into 1, and we'll just have f prime of t. Okay? Okay. Now, what is R1 of x? Well, R1 of x is, we computed this before. R1 of x R1 of x was f of x minus f of c. So the case of n equals 1 is literally the statement of the fundamental theorem of calculus. Okay? So this is a fundamental theorem of calculus, and we will talk about this in class shortly. So within the next couple of weeks, we'll discuss this in class. Now, that's the base case. And so now let's do our inductive case. So now let's say suppose it is true. Suppose nth derivative exists and is continuous on AB, then Rn of x is equal to the integral from c to x, x minus t to the n minus 1 over n minus 1 factorial, and then the nth derivative of f at t dt. And I want to show that the n plus first remainder is this with, right, put in the n plus 1. Okay, so here's how I'm going to do it. So I'm going to use integration by parts to evaluate the integral from 0 to x. This integral right here, x minus t to the n minus 1 over n minus 1 factorial, nth derivative of t dt. So for my integration by parts, u dv, right? Integral of u dv is uv minus the integral of v du. And this is something else that we'll prove once we get into our properties of integration, right? So let's see here. What do I want to be my u and what do I want to be my dv? So I think I'm going to want u to be the, u will be the nth derivative, so that my du will be the nth plus first derivative, which matches with having r sub n plus 1, right? Because I'm trying to get to r sub n plus 1 being true if the this statement being true if it's true for n, okay? So u is going to be that nth derivative of f at t, and my dv is going to be x minus t to the n minus 1 over n minus 1 factorial dt. So with that, I'll have uv And v is going to be x minus t to the n over n factorial. And that'll be out evaluated at c and x minus the integral of v du. So it'll be x minus t to the n over n factorial. That's my v. And then du will be n plus first derivative of f dt. Okay? So when I plug in t equals x, I'm going to get x minus x, that's just going to be 0, so that's going to go away. Ooh, wait a minute. I think I left off a negative sign because if this is my dv, then v would be minus x minus t to the n, right? Because the t, this is with respect to t, not with respect to x. So I'm going to go back and put in a minus sign here. And I need to put a minus sign for here, okay? Okay, so I'll get minus 0 minus, now if t is equal to c, I'll have the nth derivative at c times x minus c to the nth power over n factorial. Okay, and then that'll be plus the integral from c to x minus t to the nth power over n factorial times the n plus first derivative of f at t dt. And that is, of course, just going to be nth derivative at c, x minus c to the n over n factorial, plus integral of c to x minus t to the n over n factorial, n plus first derivative at t dt. And all of this is supposed to equal Rn. Rn, remember, by definition, is going to be equal to f of x minus, we're going from 0 to n minus 1, the kth derivative at c over k factorial, x minus c to the k. So remember, we had that slide way back in the beginning, way over yonder. We have the definition here, right? So Rn is f minus that n minus first partial sum. Okay? So this is equal to this. Okay? So what I'm going to do now is just rearrange, make it all black. And I'll say, so this minus this is equal to this. And now I can rewrite this as the sum from 0 to n, kth derivative at c over k factorial, x minus c to the k. So f of x minus this is equal to this. But do you notice this is r sub n plus 1 of x? So, just to make it very clear, r sub n plus 1 of x is equal to this, right? Which is what we wanted to show, right? Okay, and we did kind of assume when we were doing the integration by parts, in order for us to do the integration by parts, right? So when we said that this is equal, when we said that this integral is equal to this minus this, we were assuming that our n plus first derivative is integrable on that domain, okay? All right. So now you have two different versions of Taylor's theorem, one where you're given the remainder in terms of derivative and the other where you're given a remainder in terms of an integral. And feel free to use them whichever one you want, whenever you want it, right? The last thing I'm going to do is just give this corollary. So this corollary just gives a different way to write the remainder. This is called Cauchy's form of the remainder. And the proof basically uses a combination of Taylor's theorem and the intermediate value theorem for integrals. We will go over the intermediate value theorem for integrals relatively soon, so within the next week or two. All right, so that's why I'm kind of rushing over this. This is just if you're curious, right, on Cauchy's formula for the remainder. Okay. All right, that is it for this marathon lecture. As usual, let me know if you have any questions.